Hi, I'm Sarah. This is Linsig. Let's go over time invariance. Okay, the general idea here is that we have an input, x1 of t, that gives us an output, y1 of t. Then let's call another input, x2 of t, and set it equal to a shifted version of x1 of t, so x1 of t minus t naught. And what this is saying is we took the time and we moved it either forwards, backwards. This is not the same time as before, but that's the only thing that's changing. And then we see y2 of t. And what we want to know is whether y2 of t, so what happens when we put the shifted version of x in, we want to know if that's equal to y1 of t minus t naught. In other words, is shifting the input the same thing as shifting the output, if you look at the two outputs that you get? And then the way that I like to think about it is when you do the x2 of t, you lop on a t naught. And then when you go back and solve for the y1 of t minus t naught, you plug in. And this is going to make more sense once we do some examples. So that's the general idea. Let's go ahead and try this first example. This is a discrete system. We start off with our x1 of n is going to give us y1 of n, which is the same thing as x1 of n plus 2 plus x1 of n minus 2. Cool. And now we have x2 of n, which is the same thing as x1 of n minus n naught. So what we're going to do here is whenever we see an x1 of n, we're going to lop on a minus n naught. So y2 of n is going to be x1. We see an n, so n minus n naught plus 2 plus x1 of n, again, minus n naught, minus 2. And what we're trying to check here, we want to know is y2 of n. Want to know, is that equal to y1 of n minus n naught? So we take our y1 here, let's drag it back down, and we have x1. We're going to plug in n minus n naught for n. So I want you to imagine that there are little parentheses here now. And again, that'll come into play a little bit more later. So we have n minus n naught plus 2 plus x1 of n minus n naught minus 2. Lo and behold, these are equal. Yay! So our first example is time invariant. Cool. Okay, let's start on a second example. We're going to get our x1 of t. It's going to give us y1 of t, which is just x of 3t, or x1 of 3t, you could also call it. And then x2 of t is x1 of t minus t naught. And that gives us y2 of t, which is equal to x. Okay, so this is where that plug-in versus lop-on comes into play. Right now, we're just going to lop on a t naught because we're solving for x2. So 3t, and then just lop on that t naught, that minus t naught. But then we want to know, is y2 of t equal to y1 of t minus t naught? And when we go to solve for that, we're going to actually go ahead and plug in the t minus t naught. So x1 of 3, now imagine little parentheses around that t. So t minus t naught, which is equal to x1 of 3t minus 3t naught. Let's compare that to our y2 of t up here, and we see that these are not equal because the 3 wasn't distributed. So not equal, therefore time variant, or not time invariant. Okay, let's try another example. We have x1 of n gives us y1 of n, which is equal to 2 times the summation from n minus n naught to n plus n naught x of k plus 4. And now we have our x2 of n, which is x1 of n minus n naught, which gives us y2 of n, which is 2. Okay, so now we're encountering n's that aren't directly affiliated with x's. Since we're just lopping it on as we're solving for x2, or solving with x2, you're only going to put a minus n naught where you see an x of k. And if that didn't make sense, I'll show you. So we have the summation from n minus n naught. We're leaving these alone because they're not affiliated with an x of k directly, plus n naught. And we have our x over here, so we're going to do k and then just lop on the n naught plus 4. Okay, now we're going to solve for our y1 of n minus n naught. So we're going to get y1 of n minus n naught, and then we're going to plug in the minus n naught wherever we see an n. So we're going to have 2. If we look over here, if we have our imaginary parentheses drawn around that n, we're going to go from n minus n naught plus n naught to n minus n naught minus n naught x of, and this is where things get funky because there's no n here. The x of k part is not dependent on n at all. So we're just going to leave it as k and then plus 4. And now what we want to do is see if we can try to get these two to look the same. And I'm going to simplify this one really quickly to 2 times the sum from n minus 2 n naught to n, because minus and plus cancel each other out, of x of k plus 4. Okay, if we look at this one, we can actually do a variable change, and I like to use the variable, or the letter m, just cause. So we have m equals k minus n naught, and then here, the first thing you do is solve for k, because there's a little k here. The summation is going from k equals n minus n naught to k equals n plus n naught. So we're going to solve for k equals m plus n naught. And then if this were an integral, you'd also want to take the derivative of m on both sides. So you have a dm to replace the dk with, or d tau with. Okay, so now we have 2 times the summation from m plus n naught equals n minus n naught to m plus n naughts, plugging in for k, equals n plus n naught of x of m plus 4. You're always going to define your m as a thing inside the brackets, or the thing inside the parentheses with your x. So now let's simplify this down. We're replacing k with m here. So we're going to move the n naught to the other side in both cases. So this is going to give us 2 times the sum. If we move the n naught over, we're going to have n minus 2 n naught. And then up here, if we move the n naught over, we're just going to have n, because the plus and minus are going to cancel each other out. X of m plus 4. This is looking really similar to that. The only difference is that we have a different dummy variable. But the dummy variable, by definition, is a dummy variable. You can call it whatever. So we can actually just call this k instead of m. So we're going to have n minus 2 n naught to n, x of k plus 4. And now this and this are the same. Yay! And then it is time invariant. We're going to again start off just with the same formula that we prescribed for all of these problems. x1 of t yields y1 of t, which equals t x of t plus 2. And now we're going to do x2 of t equals x1 of t minus t naught. And that gives us y2 of t, which equals, okay, we're just going to lop on a minus t naught wherever we see the x of t. So t times x t minus t naught, lop that on, plus 2. But then we're going to check to see if y2 of t, whoops, let's see if that equals y1 of t minus t naught. Okay, y1 of t minus t naught. Whenever we see a t, we're putting parentheses around it and replacing it with t naught, or replacing it with t minus t naught. So we're going to have a t minus t naught, x of t minus t naught plus 2. And we see here that because of the minus t naught that is only present in the y1 of t minus t naught, it is not time invariant. All right, let's do another problem. x1 of n yields y1 of n, which equals x cubed of n plus 4. And now x2 of n gives y2 of n, which equals x3. Oops, and remember that x2 of n is x1 of n minus n naught. And that's n minus n naught plus 4. Okay, and now if we check our y1 of n minus n naught directly, then we're going to get x cubed of n minus n naught plus 4. And these are equal. Therefore, it's time invariant. So even though it's not a linear function or a linear system, it is a time invariant system. And we know it's not linear because of this x cubed up top. Okay, this one's long. We're going to start off with our x1 of t, as always, gives us y1 of t, which equals the integral from negative infinity to t plus infinity x of tau minus 4 times e to the negative 1/2 t minus tau squared, and then it's all integrated with respect to tau. Okay, and then we do our x2 of t, which is the same as x1 of t minus t naught. And that, oops, that, what am I doing? That gives us y2 of t, which is, here we're only plugging, or we're only lopping on where we see an x of t. So from negative infinity to t plus infinity, x of tau minus t naught minus x of tau minus t naught e to the negative 1/2 t minus tau squared t tau. Okay, that was long. And now let's get our y1 of t minus t naught, which equals the integral from negative infinity. Oh, we found a t already, so that's already going to be t minus t naught plus infinity. And then x of, there's a tau here, not a t, so we don't have to worry about plugging anything in here. Tau minus 4, e to the negative 1/2 t, so minus t naught, minus tau squared d tau. Okay, let's steal this part, steal our y2 of t, and see if we can make it look like our y1 of t minus t naught. So I'm going to box that in for later. Okay, first thing we do here is we're going to do a variable change. So m equals the thing in the parentheses, tau minus t naught. And then we're going to take the derivative of m, and that just comes out to d tau. I've had it come out before where it becomes negative d tau, so just keep an eye out for that. And then we're going to solve for tau. So tau equals m plus t naught. Okay, we're going to rewrite this. So the way this integral is set up is actually from tau equals negative infinity to tau equals t plus infinity. So we're going to set m plus t naught equals negative infinity, and then m plus t naught equals t plus infinity. Cool. And we're going to have our x of m here, e to the negative 1/2. We have a t minus tau, so we're going to get t minus, and then this part, minus m minus t naught, because I put parentheses around the tau, and that's going to get squared with respect to tau. Okay, I'm going to move this down for more space. If we solve for m in the bounds here, we're going to have the integral from, it's going to be t minus t naught plus infinity. The m is implicit at this point, and then we're going to have negative infinity minus t naught, which is just the same thing as negative infinity, because if you're subtracting anything from negative infinity, it's just going to be negative infinity. X of m e to the negative 1/2 t minus t naught minus m squared d tau. Does this look familiar at all? It does, except that I forgot the 4. Oh no. Okay. If we go back and we add the 4 everywhere it's supposed to be. Minus 4. Minus 4. Then, if we replace our m, which is a dummy variable, with a different dummy variable of tau, then these are going to look the same. Therefore, it's time invariant. Over here, we're going to get our x1 of t gives us y1 of t, which is the integral from 0 to 1, x of tau, d tau. x2 of t is the same thing as x1 of t minus t naught, which is, which gives us y2 of t, 0 to 1, x of tau minus t naught, d tau. This is x2 of t, that's x1 of t. But now if we solve for y1 of t minus t naught directly, we're going to put in the t minus t naught wherever we see a t. So x of tau, d tau, we just got through the entire thing without seeing any t's because it's not dependent on t. Therefore, because there's a minus t naught here and no minus t naught here, it's not time invariant. Okay, let's try another one. This one uses derivatives, but don't be fooled. It's the same procedure. x1 of t yields y1 of t, which equals x prime of t plus, x1 prime of t plus x1 of t. And then x2 of t is the same thing as x1 of t minus t naught. And it gives us y2 of t equals x1 prime of t minus t naught plus x1 of t minus t naught. Okay, and then if we plug in y1 of t minus t naught directly, we're gonna get x1 prime of t minus t naught plus x1 of t minus t naught. These are equal, therefore it is a time invariant system. Okay, one more example. This one just illustrates the importance of knowing when to lop on and when to plug in. So we're going to get our x1 of t first. That's going to give us y1 of t, which equals x1 of t minus 2 plus x1 of 2 minus t. And then we're going to do our x2 of t equals x1 of t minus t naught. We plug that into our black box here, and that's going to give us x1 of t minus t naught minus 2 plus x1, don't forget we're just lopping on, 2 minus t naught. And then if we go directly, y1 of t minus t naught, here we're plugging it in. So we're going to see an x1 of t minus 2 plus x1 of 2. Now we're going to pretend that there are those parentheses around the t. So 2 minus t, and then minus minus, so plus t naught. And because of that sign here, it's not time invariant. All right, that covers time invariance. Thank you for watching.